Chapter 2, we're going to look at matrices in much more detail. So section 2.1 is matrix operations. So in this section, the two basic learning objectives that you need to master are computing sums, products, and scalar products of matrices, and then also transposes and products of transposes of matrices. In addition, we've got some theorems and properties about matrix operations and transposes that you should be able to then reason about as a more advanced learning objective. So quickly recall that an m by n matrix has m rows and n columns, and we use the notation, the a, lowercase a, and then subscript notation to indicate the entries of the matrix. And we also use a bar sub 1 and a bar sub 2 to indicate the columns of the matrices. Okay. So the first thing we want to talk about is square matrices. So if a matrix has the same number of rows and the same number of columns, it's called a square matrix. A diagonal matrix has zeros everywhere except on the diagonal, right? So whenever you're off the main diagonal, this is called the main diagonal, then the values are non-zero, or the values are zero. On the main diagonal, you can have both zero and non-zero values. So that's a diagonal matrix. The identity matrix is simply a diagonal matrix where all the values on the diagonal are 1. We've talked about this before already. And notice that the columns of the identity matrix are E1, E2, and E3. These are going to be sort of the standard vectors for Rn when I is an n by n. Right, so we do I equals an n by n to indicate the rows and columns of I. And in general, we'll use this notation, which we've been using. Subscript of capital letters m by n tells you that that's an m by n matrix, m rows and n columns. Okay, so what can we do with matrices? Well, one thing we can do is add and subtract them. So we call this matrix arithmetic and scale them. Matrix arithmetic. So two matrices are equal if every element of the matrix is equal, and so they have to be of the same size. So a 2 by 2 matrix can't be equal to a 3 by 3 matrix. We can scale a matrix, which just means multiplying it by a scalar value out front, right? And I've got some examples here for you. Matrix addition, you just do element by element adding, right? So if you notice here, a plus b, 3 plus 2 is 5, 2 plus 2 is 4, 1 plus 2 is 3, and so on and so forth. We have the zero matrix. This is the matrix for all zeros, right? And basically a plus the zero matrix is equal to a. And here's some rules, right? So a plus b is b plus a plus b plus c is a plus b plus c, and so on. So probably should know these. Matrix multiplication is a little different beast. So the product matrix A times matrix B is defined only when the number of columns in A is equal to the number of rows in B, in which case A and B are then called conformable matrices. So matrices that can't be multiplied are called non-conformable matrices. And the product AB will have the same number of rows as A, but the same number of columns of B. Right, so I've written that out for you here, and you'll notice that these two numbers have to be the same. Right? So the columns of A have to be the same number as the rows of B. And the resulting matrix will be m by r. Right? Let's draw a little arrow over here. So if you kind of keep that in mind, you really won't get in trouble. So notice here I have a 2 by 2 and a 3 by 2. This is undefined because they're not conformable, right? Because the number of columns of A is not the same as the number of rows of B. So let's define how to compute, or define what we mean by matrix multiplication. So if A is an n by n matrix and B is an n by p matrix with columns B1 through BP, right? So notice that we've defined A and B to be conformable. Then AB the product AB is an M by P matrix where the columns are A times B1, A times B sub 2, and so on, right? So I've kind of written that out. The first column of the product AB is the vector product matrix with B1. Second one's going to be the matrix vector product A with B2, and so on, right? So if I have just two simple matrices here, so I've now made them conformable, right? I just turned the two around from a minute ago. So notice the number of columns in A is equal to the number of rows in B, right? Then I'm going to do, this is A B1, and this is A B2, and I take those two columns and I make a matrix, and that's the product. Okay, that's a little tedious for computation, so there is really an easier way to do this, and that's called the row column sum or the row column rule for computing A times B, and this is the way you're going to do it most of the time. Okay, so here what we're going to do is we're going to say I'm going to take the first row of A and the first column of B, and I'm going to multiply the components. I'm going to do 1 times 3 plus 2 times 1. So here I've written that out. All right. Then I'm going to repeat that process, and I'm going to erase this. Now I'm going to move over, and I'm going to do the first row of A times the second column of B, right? And that'll be 1 times 4 plus 2 times 2. And here's that one. I'm out of columns of B. Time to start over. Second row of A, now with the first column of B. So that's 4 times 3 plus 5 times 1. There it is. Now I'm going to do second row of A, second column of B, 4 times 4, 5 times 2. I think you see the pattern here. Right, so this is the way to perform matrix multiplication once we do this. This is more efficient than doing the matrix vector products. A couple of notes of very importance. Matrix multiplication does not commute. A times B is not always equal to B times A. In general, if A times B is equal to A times C, that does not necessarily mean that B and C are the same. Okay? It can be the case, but it's not always the case. And in general, if A times B is equal to the 0 vector, that does not mean that either A is 0 or B is 0. So, all right. And here's some algebraic rules for matrix multiplication. Shouldn't be any surprise to you here, right, that you can do the matrix multiplication in any order. There are some rules about efficiency in terms of whether to do this A times B first and then multiplied by C, or to do B times C and then multiplied by A. We won't get into that. We won't be working with matrices that large, but know that those algorithms exist. Okay, so another operation that we might be interested, or another operation on matrices, is the transpose of a matrix, and this just means switching the rows and columns. Okay, you'll eventually see us do a few things that are interesting with this when we get to least squares. All right, so here I've transposed the matrix, and notice I've just taken this first row became the first column, second row became the second column. That's the transpose. Here's some rules. The transpose of the transpose gets you back to the original matrix. Would hope so. If you have a scalar, right, alpha times A, you can slide the alpha out front and perform the transpose and then scale. A plus B transpose is A transpose plus B transpose, and here's the one that's odd. AB transpose is not right, is B transpose A transpose. So AB transpose is not equal to A transpose B transpose. Now there are cases where that is so, but in general that is not always true. Finally, matrix power. So if I raise a matrix to a power, that just means multiply it by itself over and over and over again, right? That only works for square matrices, right? Because if you have a non-square matrix, then a squared may not even be defined. So we just talk about matrix powers for square matrices. In here, I just gave you some examples of matrix powers. So read the section in the book and then work some of the practice problems.